So this lesson is evaluating limits by using substitution. If I want something like this, the limit as x approaches 3 of 2x squared minus 5x plus 1. I recognize that is a polynomial, and one of our rules of limits tells us we can evaluate the limit of a polynomial just by plugging in the number. And the fact is that rule extends to any continuous function. All polynomials are continuous functions. So what do we get? We get 2 times 3 squared minus 5 times 3 plus 1, and the result is 4. So just to kind of verify that, we could take a quick look at the graphing calculator. And plugging that in, y equals 2x squared minus 5x plus 1. And looking at values from the table, make it ask. I want to choose numbers near 3. So choosing numbers near 3 like 2.9, 2.99, 2.999. And you can see what are the y values, what are the values of the function getting closer and closer to. Certainly you could believe it's getting closer to 4, but it's not enough to approach from the left. You've got to also approach from the right. 3.1, 3.01, 3.001. And again, you see getting closer and closer to 4. So that reinforces what we did symbolically. So again, our rule tells us things like the limit of the sum is the sum of the limits, the limit of the product is the product of the limits. You can evaluate the limit of a polynomial just by plugging things in, but it goes beyond polynomials. Like I said, for any continuous function, this rule will work, and practically that's what we do. So if I want something like the limit as x approaches pi over 4 of x sine x. So what we do is we plug in pi over 4 and see if it seems reasonable. Well, what do I get? I get pi over 4 times the sine of pi over 4, which would be pi over 4, times pi over 4's sine is either 1 over root 2 or root 2 over 2. I'll stick with that version. So we'll say we get root 2 pi over 8, which is kind of interesting. Now, how might I use that, or how might I check that? Let me go ahead and look at Desmos this time and use that to reinforce our notion. So I will go ahead and I will put in the function f of x is x times sine x. But I'm going to need to work with my window. So let's make each step maybe pi over 4. So I use this down here for pi over 4. And let's see if that's good enough. Can't quite see it, but interesting looking graph for sure. Here we go. Here is what's happening as we're getting closer in view, so we can actually visualize where pi over 4 is. As I'm approaching pi over 4 from the left, where are the y values headed? Well, getting closer to something like, it's hard to tell, but something in the 0.5 range. So if I zoom it in, getting closer to pi over 4, 5498 from this side, 5655 from that side. Zoom it in even more if we can. We can see our pi over 4, zoom it in even more. So as we approach pi over 4 from the left, 5537 from the right, 556. So certainly something in the 55 area. Now, when we did it by hand, we did it with plugging in, we thought it was root 2 pi over 8. So let's jump to the graphing calculator and see if that's in the 0.55 range. So we want the square root of 2 times pi divided by 8. And we hope it's around 0.55 based on our picture. And sure enough, it is. So that reinforces our work. And again, the issue is we have a continuous function. So it is fair for us to plug in values. Now, where does this fail? This fails if I have a question like this. The limit as x goes to 3 of x minus 3 downstairs. So right away, we know 3 is not in the domain. And for the sake of interest, let's put x squared minus 9 upstairs. So if I plug 3 in, I get 3 squared minus 9 over 3 minus 3. I'm not going to write equal because that would be incorrect. Over here, though, I'll write equal. 0 over 0. Now, we need to talk about 0 over 0 because we cannot evaluate this using the plug-in method. Using substitution. And again, the reason is because the function is not continuous there, which we'll formalize in a later video. Because you can't divide by 0, but I want to look at something. 0 over 0 is a different concept than, let's say, 5 over 0. So a little informal mathematics here. 6 divided by 2 is 3. Why is that? Because 3 times 2 is 6. Right. I don't know. What can we say? 63 over 9 is 7. Why is that? Because 7 times 9 is 63. But if I have 5 over 0, I would need some number here times 0 to equal 5. Whatever number goes here, right? 3 times 2 is 6, 7 times 9 is 63. Some number times 0 equals 5. Well, that'll never happen. But 0 over 0 is a different thing. If I have 0 over 0 equals some number, I need that number times 0 to equal 0. And you recognize, in a sense, that could be anything. So if I have a 0 over 0 case, there is a chance I might have a limit. I don't know. I can't use this technique to find it. But if I have a 5 over 0, I've got no chance. It can't be a limit. So let me show you what I mean by that. If I am looking something like this, what is the limit as x goes to 4 of x minus 4 downstairs? So we have a 0 downstairs, and let's say x plus 1 upstairs. When I plug that in, what do I get? 4 plus 1 is 5 over 4 minus 4. I get 5 over 0. So that can have no limit. So our conclusion here is to say the limit does not exist. So always a good idea to visualize that or to use the graphing calculator or something to get a feel for it. So let's jump to the graphing calculator this time. And I'll take a look at x plus 1 divided by x minus 4. X plus 1 divided by x minus 4. And I want to get closer and closer and closer to 4. So what am I going to do? I'm going to go to my table. We'll make it automatic first to clear what was there before. And then we'll go to ask, second table to ask. And we'll plug in numbers near 4 and see what happens. Second table, near 4, 3.9, 3.99, 3.999. Well, this is certainly not stabilizing. So as I approach 4 from the left, this appears to get very large negatively. What does that mean? The limit as x approaches 4 from the left of this, it's tending to negative infinity. Most authors just say it equals negative infinity. I'm not thrilled with that, but I'll stick with the convention. If I approach 4 from the right, what do I get? 4.1, 4.01, 4.001. And you can see those numbers are getting very large on the positive side. So if that's the case, what am I going to say? I'm going to say the limit as x approaches 4 from the right of x plus 1 over x minus 4 equals positive infinity. Well, either way, if you get infinite on either one of these, that limit does not exist, right? So the limit as x approaches 4 of that certainly does not exist. Where this gets tricky for some students is when I have a situation like the following. If I want to take a look at something like, let's put x minus 2 squared downstairs, and I don't know, x minus 3, and I want the limit as x approaches 2. So we're going to try to plug it in and see what happens, right? Plug in the 2 minus 3 over 2 minus 2 squared, negative 1 over 0 squared, negative 1 over 0. So I'm not happy with that. No limit. The limit does not exist. But I want to show you something. What happens as I approach 2 from the left? What happens as I approach 2 from the right? What is the limit as x approaches 2 from the left of x minus 3 over x minus 2 squared? So I'm going to choose numbers to the left of 2. We're going to try to see what happens. So again, I will jump to the graphing calculator and we'll clear all this out, or I can just type over it, I guess. To the left of 2 would be 2.9. Excuse me, not 2.9, 1.9. Try that again. 1.9, 1.99, 1.999. Oh, of course, I forgot to change the original question. That's important. Let's go ahead and change the original question. Upstairs, x minus 3 divided by x minus 2 squared. And now I can go back, look at my table. 1.9, 1.99, negative 110, negative 10,000, negative 1, followed by 6 zeros. That's heading to negative infinity. All right. So this is heads to negative infinity, which most authors say that limit is negative infinity. That does not mean it exists, but it's heading towards negative infinity. The limit as x approaches 2 from the right of x minus 3 over x minus 2 squared. Again, we have negative 1 over 0, so we know there is no limit. We're approaching 2 from the right this time. 2.1, 2.01, 2.001. Notice also heading towards large negative numbers. So as we approach from the right, we can also say that's negative infinity. So therefore you could argue, you could say using the standard notation, that the limit as x approaches 2 of x minus 3 over x minus 2 squared equals negative infinity. But I want you to say these do not contradict each other. The limit is negative infinity and the limit does not exist. Those are both true statements. So be careful to see what the question is asking. And let's finish this up by just taking a quick look at Desmos. What does this graph look like? So if I have x minus 3 over x minus 2 squared, x minus 3 in parentheses on top, divided by x minus 2 squared. And we want to look at our standard zoom, and it looks like that. You can see, and we'll change this, of course, to stepping 1 instead of stepping pi over 4. And you can see that as we head towards 2, on the left side it heads to negative infinity, on the right side it heads to negative infinity. So the limit as x approaches 2 of this thing will indeed be negative infinity, but that limit does not exist. It is not a a real number. Let's just finish this off with another standard question where it actually works. So if I want the limit as x approaches 1 of 2x plus 3 over x squared plus 5x plus 4, we know the limit of the quotient is the quotient of the limit. So if we wanted to, we could use our formal rules and say limit as x goes to 1 of 2x plus 3 over the limit as x goes to 1 of x squared plus 5x plus 4. And then we could recognize these are both polynomials. You could plug them in, or you could say the limit of the sum is the sum of the limits, and you could use all of these rules of limits. But you can see the process still comes down to the fact that these are both nice functions. I can plug numbers in. 2 times 1 plus 3 on top. 1 squared plus 5 times 1 plus 4 on the bottom. 2 plus 3 is 5 on the top. 1 plus 5 is 6 plus 4 is 10 on the bottom. And we get 1/2. If the function is nice, i.e. continuous, i.e. no breaks, no holes, then you can just go ahead and evaluate the limit by plugging numbers in. And that'll finish this lesson.